All right, guys, let's start. So now we are doing your lesson number 2 of your partial differential equation, right? So in your lesson number 2, what is important to understand is that it's basically it's talking about basic methods to solve your partial differential equations, right? So in this chapter, right, or this lesson, right? In this lesson, we are actually studying about Milstein scheme, right? Where the main idea is about simulating the stochastic path more accurately than Euler. You have to look at the finance connection that it's using your Monte Carlo pricing, Greeks, war, exposure simulation. Then we'll also see about your separation of variables, which is about turning a PDE into your simpler ODEs. We will use that for heat equation, transform Black-Scholes, partial differential equation. We'll also use that for method of characteristics. Main idea is to solve first order PDEs along curve. The finance connection is transport equations, forwarded dynamics. Then we have methods such as Green's function, which is to solve PDE using your impulse response, and we'll use for pricing kernels, option valuation by integration. We have also your numerical PDE methods. Main idea is to approximate PDE on a grid or mesh, used for American option, exotic option, multi-factor models. Then the method is summary and kind of practice, which will reinforce the idea, and we'll look at the exam of the practical quant finance application, right? So this lesson is about basic methods of solving your partial differential equations or PDEs. In quant finance, PDEs appear because many pricing and risk problem ask how does the value of a financial product change when time passes and market variables move. For example, an option price depends on your V is equal to VST, right? V is a function of stock price and time t. A PDE then tells us how V changes with respect to both S and T. That is why PDEs are central in option pricing, hedging, risk management, and dynamic portfolio optimization. Okay. Then we look at next slide, right, which is Milstein scheme, which is implementation 1, right? The slide gives the Milstein discretization for simulating an stochastic differential equation. The equation is given in front of you. You look at this equation closely, right? What is this equation telling us? This equation is basically giving us xn plus 1 equals xn plus drift a of xn times delta t plus diffusion b of xn times delta w n plus 1/2 b of xn times b prime of xn times delta w n squared minus delta t, right? The Brownian increment is your delta wn is normally distributed with mean 0 and variance delta t. In your Python style simulation, right, it is dw is equal to your okay z basically m0. So the random shock is scaled by your delta t, not by under root of delta t, not by delta t, right? So here, if you look at closely, right, what is ax and delta t? This is basically your drift component. Financial interpretation is that expected movement in asset price, rate, volatility. Then we have your vxn dw, which is random shock, basically market uncertainty. Then we have half of this thing, right? In fact, if you remove xn and if you just take half bb dash dw square minus delta t, right? This is basically Milstein correction, right? Captures your curvature from state-dependent volatility. Why this matters in quant finance? Because if we simulate stock prices or interest rate or volatility or credit spread, better path accuracy improves Monte Carlo pricing, Greeks, XPA, exposure profile, VAR, and expected shortfall calculation. One important point is this slide is technically about stochastic differential equation simulation, not directly solving a partial differential equation, but it connects strongly to your partial differential equation through the Feynman-CAC idea that many PDE pricing problems can also be solved by simulating the corresponding SD, right? So that is the Feynman-CAC idea, right? So please remember that key idea uses the same random increments Euler, Merrioma, adds a correction term to capture quadratic variation, improves the path accuracy of simulations, right? Then we get into the next term. We look at your Milstein scheme implementation too. The slide explains each term in the Milstein formula. The drift approximation is given, which is a of x n times delta t, approximate the integral form t n to t n plus 1 of a of x is ds, right? This is the deterministic part. The diffusion part is given below, right? The diffusion approximation is given bxn delta wn approximates to integral of bxs dws from tn to tn plus 1. That is the stochastic part. The Milstein correction is also given, this part. This correction comes from the Ito's Taylor expansion, right, which is given here. And in simple word, when volatility depends on the state variable, the part does not move linearly. The Milstein term adjusts for that temperature. The slide says Milstein improves strong convergence from half to 1, right? Meaning path by path simulation accuracy improves. Calculates local quadratic variation. When we have model, the specific rate model, diffusion constant sigma is b dash x 0x, Milstein benefit same as Euler. GBM stock model sigma s is b dash x 0, no. Milstein benefit, Milstein adds correction. If model is CIR model, diffusion dx is sigma under root r is b dash x 0, no. Milstein benefit, Milstein can improve path accuracy. Key takeaway is b dash x is equal to 0, Milstein, Euler, Merrioma. So Milstein most useful when volatility is state dependent. Okay. And then we have your implementation node that a b dash x is equal to 0, constant diffusion, Milstein is equal to Euler, Merrioma, right? Then we get into the next part, which is separation of variables. We look at method overview. Now we move to actual PDE solving method. The method assumes the solution can be written as this equation u of x and t equals capital X of x times capital T of t, meaning we split the solution into part x, which is the space state variable, shape across asset price, log price rate, t time, how that shape evolves over time. The idea is simple. Assume your u of x t is equal to x tt into the PDE. Substitute into the PDE, rearrange on one side depends only on x, the other only on t. Set both sides equal to a constant, solve 2 ODs instead of one PDE. This works best for linear PDE with simple boundary condition. The financial connection here is after transformation, the Black-Scholes PDE can be converted into something like a heat equation. Separation of variables gives intuition of how often values evolve through time. Right? So rearrange terms of each side depends on only one variable, set both sides equal to a constant, solving the result of ODE. This reduces the PDE into 2 ODs, right? Then we have separation of variables, heat equation. Example is one-dimensional heat equation. The slide introduced the one-dimensional heat equation, which is given mu u divided by mu t is equal to alpha sigma square u, not sigma square, del square u del x square, pronounced as simple terms. Partial u by partial t equals alpha times partial squared u by partial x squared. You have uxt, which is temperature, or in finance a value function, alpha greater than 0, diffusion coefficient, x space state variable, t time. In physics, heat spread over space. In finance, option value spread or smooth across possible asset price because of uncertainty. Assume uxt is the temperature, a value function. Alpha greater than 0 is the diffusion coefficient. Assume separable solution uxt is equal to xxt, right? And sigma square u is equal to x double dash x tt. This means here t dash t means first derivative of t with respect to time, and x double dash x means second derivative of x with respect to x, right? That is what we need to understand. Then we get into next part, separating the PDE into ODEs, substitute the separable form into the heat equation, right? You have xx t dash t alpha x double dash x tt. Now divide both sides by your alpha xx tt, right? And we get 1 by alpha t dash t divided by tt, x double dash x xx. Okay, we get 1 by alpha t dash t divided by tt equal to x double dash x divided by xx. The left side depends only on t, the right side depends only on x. For this equality to hold up for every x and every t, both sides must equal a constant. 1 by alpha t dash t 1 by alpha tt is equal to x double dash x is equal to minus lambda. So basically 1 over alpha times t over t equals x double prime over x equals minus lambda. Why I use minus lambda? Because for the heat equation, we want decaying exponential solution. Heat dissipates in finance and uncertainty smoothly pay off as we move backwards from maturity that we have. So left hand side depends only on t, right hand side depends only on x. So lambda greater than 0 is the separation constant, right? So that's okay. Then we get into the next part. We are looking for ODEs for time and space components. You obtain two ordinary differential equations, spatial ODEs, temporal ODEs, right? So from your equation, x double dash x divided by x is equal to minus lambda. We get the spatial ODE, which is this form, right? Then we get from equation your 1 by alpha t dash t divided by t equal to minus lambda, right? We get the time ODE t dash t is equal to 1 alpha lambda tt is equal to 0. The solution for time is tt is equal to c exponential minus alpha lambda t, pronounced as t of t equals c times e to the power minus alpha lambda t. The final solution is written as a sum of u xt is equal to summation of n a n x n x exponential minus alpha lambda n t u of x and t equal the sum over n of alpha n times x n of x times exponential to the minus alpha lambda n t, right? Interpretation here is x and x, right? This part x and x is the spatial pattern of your sine or cosine lambda n. Lambda n is the eigenvalue. This whole thing minus alpha lambda n t is equal to time decay, right? This is your time decay. an is basically the weight determined by initial boundary condition. The financial intuition here is the payoff can be decomposed into many modes, higher frequency modes, decay faster. That is why optimal value becomes smoother as we move away from maturity, right? Coefficients an are determined by boundary and initial conditions. Then we get into next part, which is the method of characteristics, which is the method overview. The method of characteristics used for first order PDE, especially hyperbolics, partial differential equations. The key idea is convert the PDEs into ordinary differential equations along spatial curves called characteristics. Characteristics are path only along which the solution behaves simply in finance. This is useful for transport type equation, forwarded dynamics, and simplified pricing equation where information moves along a direction, right? Such as maturity or time to expiry. When we look at PDE type basically heat, parabolic PDE, main behavior, diffusion, and smoothing. Suitable method are separation, green function, FDM. Then we have first order transport PDE, main behavior is movement propagation, suitable method characteristics. Then we have complex pricing PDE, main behavior is no closed form. Suitable method is numerical methods, right? So method of characteristic is a powerful technique for solving first order partial differential equation, especially hyperbolic PDEs. The idea reduce a PDE to the system of ordinary differential equations, solve the ODs along special curves called characteristics. Along these curves, the PDE solution behaves like an OD. Interpretation characteristics represent path along which the information propagates. Common in transport equation, conservation law, and finance. Financial elements used in simplified pricing equation, forwarded dynamics, and transport type PDEs. Okay. Then we get into the next part, method of characteristics, PDE setup. Example, first order linear PDE, right? The slide gives you the first order linear PDE, partial u by partial t plus c times partial u by partial x equals 0, where u xt is unknown function, c is the constant propagation speed, fx is the initial profile. Initial condition is this, right? Ux comma 0 is equal to fx. This means at time 0, the shape of the function is known, right? The PDE says the profile moves along the x direction at speed c without changing shape. And the financial example is a term structure curve can roll through time. Some PDE describe how information moves along the maturity dimension, right? So this is what we are looking at. This equation describe the transport of the quantity used with speed x along the direction. Okay. Then we get into the next part, which is the method of characteristic solution. The characteristic equation are obtained by this two formula, dx by dt is c and du by dt is 0. The first equation says the characteristic curve moves with speed c, right, which gives us this. The speed u is constant along that curve, right? So u x tt is constant, so x minus ct is constant. The general solution is uxt is equal to fx minus ct, meaning the initial profile fx moves to the direct right with speed c without distortion. In finance language, the initial curve with the yield curve, forward curve or exposure profile. The method tells us how the curve shifts through time under a transfer equation. Okay. Then f is determined by the initial condition. Interpretation is the initial profile of fx propagates without distortion with speed c. Then we get into the next part, which is basically looking at the Green's function method. Now, see, Green's function is a beautiful idea. You solve a complicated linear partial differential equation by understanding the response to a single point impulse. The slide gives you Green's function is the impulse response of the system. Imagine dropping 1 unit of heat at one point. The Green function tells us how that heat spreads. And for a general source, we add up many small impulses using integration. The financial interpretation is Green's function concept, impulse response. Financial equivalent is pricing kernel transition density. Then we have source term. Financial equivalent is cash flow, payoff, forcing term. Green's function concept is superposition. Financial equivalent is value is sum integral of discounted future outcome. Function concept is heat kernel distribution of future state variable. This is closely connected to pricing by expectation, right? So key idea, interpret the PDE as a linear system, study the system response to a point impulse, build the general solution by superposition. Interpretation Green function is the impulse response of the system, which I told you, shows how the unit source as a point affect the solution, and financial equivalence used in option price. Heat type PDE, the linear pricing operation by convolution representation. Then we get into the next part, which is Green functions mathematical definition. The linear PDE is written as your L operator applied to U of x and t equals f of x and t. Here L is the linear differential operator, fxt is the source term. Your G, your x comma t, you have different symbols here, right? So basically, if you look at it, this equation, right? What is happening here? L applied to G, right, of x, t, z. This is pronounced as z, right? Z. Tau. This is pronounced as tau. Okay. Equals delta of x, z times delta of t minus tau. Here's z and tau are important. Once G is known, G, right? G is known, the solution is given here. This is convolution. We multiply the source by the system response and integrate over all previous time and location. So that is 0 to t and minus infinity to infinity. This is the integration. The convolution of the source with the Green's function. Where if you look at this, right, in this, where we applied the operator, right, again, we said delta, right? This one is the direct delta function, right? So remember that. Again, it's a complex equation. Please understand this. Then we get into slide number 13. We are looking at heat equation. The heat equation with the source is given by this equation. The Green function is for the one-dimensional heat equation is given by this function. So G of xt z tau equals 1 over square root of 4 pi alpha times t minus tau multiplied by exponential of minus x minus z squared divided by 4 alpha times t minus tau. This is a Gaussian kernel. Gaussian kernel. The right interpretation is, if you look at this part, right? If you look at this part, 1 by your under root 4 divided by 4 pi alpha t minus tau. This is normalizing factor, right? This is called normalizing factor. Okay, and then this part is called your Gaussian decay, right? T minus tau is your time available for diffusion and alpha is the speed of diffusion. The finance connection here is after transformation, the Blackfield equation resembles the heat equation. The Green function acts like your transition density. Option price becomes an integral over possible future paths or payoffs. Right, represent diffusion of a point heat source and variance grows linearly with time. Okay. Then next part is we're looking at the final solution. So for source term only, the equation is given with initial condition u x naught is equal to u naught x. The solution becomes this, right? The first integral carries forward the initial condition, second integral can add the effect of future source term, right? So this is carry forward with the initial condition, and then this is adding the future source term, right? Financial interpretation is initial condition is U naught, payoff at maturity for initial value function. Then we have Green's function G, which is transition decay or pricing channel. Then we have source F, cash flows, dividend, coupons, external forcing, integral, period average over states and time. That is why Green function connect naturally to risk neutral valuation, right? Explicit solution representation, linear superposition principle, strong intuition for diffusion and smoothing. Okay. Then we have numerical methods for solving PDEs. This slide is explained by numerical methods are needed. Why many finance PDEs do not have closed form solution. When you look at your problem, your American option, why closed form fails because early exercise creates a free boundary. Barrier option, boundary conditions are path dependent. Asian option, payout depends on average price. Lookback option, payout depends on lags, mean path value. Stochastic volatility, most state variable. Interest rate model, multiple factors and term structure. Numerical methods approximate the PDE by discretizing the time and state variable, replacing derivatives with algebraic expression, solving the resulting system. Two methods introduced here are your finite difference method and your finite elements method, right? The finance use is production pricing libraries, Greeks, hedging, model validation, risk board, and stress testing, right? So that is what we are looking at in many practical problems in quant finance. Closed form solution to PDEs do not exist. Typical example, American option, exotic option, multi-factor models, right? Numerical methods approximate the continuous PD by discretizing the time and state variable, replacing derivative by algebraic expression, solving the resulting near nonlinear system. Okay. Then we get into your finite difference method, FDM. Basically, the finite difference method uses a grid points are UXT in defined grid price XI is equal to I delta X Tn and delta T here UIN. You have to understand UIN UXI Tn. UI superscript n is the value of u at grid point x, I, and time tn. First order spatial derivatives when we look at, which is this. Okay, second order spatial derivatives when we look at this. Time derivative, we look at this. In finance, think of grid dimension. Xi is basically option pricing, meaning stock price, log price, rate, volatility. Tn is the timestamp. UIN is the option value at that grid point, boundary condition, value extreme, stock shock, stock prices, terminal condition, payoff maturity. For example, for a call option, VST is equal to max S minus K, 0. This terminal payoff is based on the final time rate and the PDE is solved backwards, right? FDM converts the PDE into a system of algebraic equations. Then we have your Crank-Nicholson, right? Crank-Nicholson method for the heat equation. The heat equation is given this way, right? Partial derivative of u divided by partial derivative by t, alpha partial derivative square of u divided by partial x square, right? Crank-Nicholson approximate the time derivative using an average of the spatial curvature at time n and time n plus 1, right? This is the equation, the change in u over one time step equals alpha over 2 times the average of the second spatial difference at the new time level and the old time level, right? The key property is we have second order accurate, meaning more accurate than basic implicit or explicit schemes, unconditionally stable for heat equation, does not blow up merely because time step is large, requires linear system, need matrix solution at each time step, used in Black-Scholes, PDE, very common in option pricing. Finance connection is Crank-Nicholson is widely used when option pricing PDEs need stable and accurate values across many asset price grid points. It's especially used for vanilla and some exotic options. Okay, so that is what we have. Then we get to next method, which is your finite element method, right? Finite element method approximates solution using small pieces called element instead of using a sample or a simple rectangular grid, which is used in your finite difference method. Finite element method divides the domain into a mesh, right? Step is divide domain into elements, create a mesh, use local basis function. Local basis function approximate solution piece by piece. Form is weak integral form, convert PD into integral equation. Assemble global system, combine all pieces, solve, get approximate solution advantages. You have complex symmetries. Why useful? Because handles irregular domains, flexible boundaries, useful for strange payoff regions. Higher dimensions can adapt better than simple grids. Finance uses. Financial problem, you have multidimensional PDEs, your finite element method. Usefulness is multiple risk factors. Then we have free boundary problems, American style exercise. You have irregular payoff domains, complex derivatives, control problems, portfolio optimization, HGB equation. FDM is usually easier and more common for standard option pricing, finite element method becomes attractive and the domains of boundary become complex, right? So remember this key step, uh, finite element methods approximate solution by piecewise basis function, which I told you, over small subdomains I told you. Divide the domain into elements mesh. I told you approximate solutions using local basis function, formulate weak integral form of the PDE, assemble and solve. Advantages: handles complex geometries, flexible boundary condition, well suited for high dimension using finance. Multidimensional PDEs, free boundary problems, and regular payoff domains. Okay. With this, we enter the summary. The key takeaways: solving a PDE. In this lesson, we introduce the fundamental method used to solve partial differential equations in quantitative finance, analytical techniques for separation of variables, method of characteristics, green function, separation of variables for linear PDE with simple geometry, method of characteristics for first order hyperbolic PDE, green function approach for linear non-homogeneous PDEs, numerical techniques, finite difference method FDM for time space discretization, Frank-Nicolson scheme for stability and accuracy, finite element method for complex multi-dimensional problem. These methods provide the mathematical foundation for option pricing, vanilla exotic, risk management and hedging, control, portfolio optimization and control problems. In next session, we will apply these PDE solving techniques directly to financial model, right? That is what the aim is. So basically, the lecture summarizes the method. We have analytical category, in which we have separation variable best for linear PDE, simple geometry. In analytical category, we have characteristics method, which is for first order transport PDE. Analytical category, we have Green's function also, which is for linear non-homogeneous PDEs. Then we have numerical method, which is FDM, right? Okay, finite difference method, which is for standard option pricing grids, especially for American option. Then we have numerical category, we have Frank-Nicolson stable and accurate pricing, and then we have FEM, finite element method, which is complex high dimensional domain, right? So the slide also says these methods support option pricing, risk management, and hedging, portfolio optimization and control problem. That is the key bridge. PDE methods are not abstract math here. They are the machinery behind pricing of weeks, hedging, stress testing, and dynamic investment decision. Okay. With this, we move to the question, guys. We have few questions here. This question tests the analytical part of the lecture. Question 1 is solving the heat equation by separation of variables. Right, solve the heat equation using separation of variable with homogeneous boundary condition. Question number 2 is about show that eigenvalues are derived from this to derive the eigenvalues. Question number 3 is explain why separation of variable fails for nonlinear PDEs. Basically, explain the failure of nonlinear PDEs. And question number 4 is apply separation to transform Black-Scholes PDE. Right, this is the closed form analytical side of PDE solving. The main message is if the PDE partial differential equation is linear and can be transformed into heat equation, we may get analytical or semi-analytical solutions. Okay. Then we have question number 5 and to 8, right? These question test the remaining method, solve transport PDE using method of characteristics, right? Question number 6, define and derive Green's function for the heat equation. Question number 7, derive explicit finite difference scheme and explain stability. Then we have explained why analytical methods are required in finance PDE. The slide moves from analytical methods to practical computational finance. In real quant finance, question 8 is the most important practical question, right? This is the most important practical question. Closed form solutions are rare, so numerical method become kind of essential. Okay. Now we have the solution, guys, we have to see, right? So then we have question number 1, which was heat equation with homogeneous boundaries. Assume your uxt is equal to xxt, right? Substitute into your what you say, substitute this into your this form. Once you substitute into this, we get this equation, right? Divide like this, t dash by alpha t, x dash by x alpha, x double dash by x, get minus alpha lambda. This gives 2 ODEs, which are these ODEs with homogeneous boundary condition. Usually your u0t is equal to 0 and ult is equal to 0. We get your xnx is equal to sine n pi x by l, right? And your lambda n is equal to your n pi L square, right? So final solution is this. Here, Vn depends on the initial condition. What is the financial interpretation here? Why are we studying here? Because this is like decomposing a payoff into sine wave components. Then each component decays over time. In option pricing, payoff share becomes smoother because diffusion reduces sharp features. Okay. Then we get into the next parts. You have solution for question number 2. We are looking at now your, in fact, 2 and 3, right? We start from this equation, x double dash plus lambda x is 0. General solution is this, right? Xx is equal to a sine under root lambda x is equal to b cos under root lambda x. Boundary condition is x0 is equal to 0 implies b is equal to 0 because cos 0 is equal to 1. Then xl is equal to 0. Sine and root lambda L is equal to 0. So lambda L is equal to n pi. Lambda n is equal to n pi by L square. Lambda n equals n pi over L, the whole thing squared. For question number 3, the key point is that separation of variables works well for linear PDEs. It usually fails for non-linear PDE because non-linear terms couple variables. For example, your u2 ut plus ux is equal to 0, right? So if your if u is equal to xx t, then ux xx pt dot x dash x t t, right, is equal to x dash x t square t. Okay, now the x part and t part are mixed in more complicated way. Important clarification here is that if slide phrase kind of appears to suggest you that u square is not equal to x squared t square mathematically, u square is equal to x square t square when u is equal to xt. The real point is not the square itself is impossible. The point is that non-linear terms destroy clean separation and superposition. Financial connection here is many portfolio optimization PD, especially Hamilton, Jacobi, Bellman equations are non-linear. That is why numerical methods are often needed in dynamic portfolio optimization. Okay. Then we get into your next part, which is your slide number 24, which is the solution for question number 4 and 5. The slide says under the transformation x is equal to natural log of s, tau is equal to t minus t. The actual becomes your partial differential of u and partial differential by tau is equal to half into sigma square. Partial differential square of u divided by partial differential square x of square, right? This is the heat equation type PD. Partial u by partial tau equals 1/2 sigma squared partial squared u by partial x squared. S equals stock price, x is equal to ln s log stock price, tau is equal to t minus t time to maturity, sigma is equal to volatility. This is the deep connection between Black-Scholes and the heat equation. In the full Black-Scholes transformation, we usually also apply scaling discounting transformation to remove the first derivative and discounting term. The slide presents the simplified heat equation form, which is enough for this lesson, right? For question number 5, please understand the characteristic functions are, dx by dt is equal to 2, du by dt is equal to 0. So uxt is equal to sin x minus 2t. This corresponds to a transport equation where the initial sine wave moves with speed 2. The financial interpretation is the profile is shifted through time without changing its shape. This is useful in simplified transport models, forwarded evolution, and deterministic roll-down intuition that we need to understand. Okay. So please understand, two questions are given here, right? So in fact, here also, this was question number 3, right? This was question number 2, then question number 3. And here also, this was question number 4, discussion in question number 5. Okay. Then we get into your solution for question number 6 and 7. The green equation to the heat equation is given this way. Then this solution is also given. This says the solution is the initial condition smoothed by Gaussian heat kernel. Finance interpretation is the option values like a weighted average of future payoff values where weight comes from the transition density. The explicit finite difference scheme is given like this. You can rearrange this, right? You can get ui n plus 1 equal to ui n plus r u n I plus 1 minus 2 ui and plus ui and minus 1, where r is equal to your alpha t. Okay, from the one-dimensional heat equation, explicit FDM is stable only if your are 1/2, meaning your alpha okay. From the financial interpretation, if the time step is too large related to the asset price with spacing, the numerical option price can become unstable or oscillatory. That is why practical pricing engines use implicit or Frank-Nicolson methods more often than purely explicit schemes. Okay. So this is for question number your 6 and 7. Okay. Question number 6 and 7, we have Green's function and your explicit, finite difference, right? So this was 6 and okay. Then we get into your question number 8. Why numerical methods are required? Closed form solution failed because of part dependence, Asian barrier, look back option, free boundaries, American option, high dimensional state space, stochastic quality, interest rate, multi-asset derivative. So we use numerical tool, finite differences, main use PDE grade, option pricing, Monte Carlo, high dimensional simulation, fluid method, fast pricing when fictitious functions are known, FEM, finite element method when complex binaries and domains. This is the practical quant finance conclusion. Closed form solution are elegant, but real pricing and risk system need numerical methods. For risk management, numerical PDEs help calculate Greek stress scenario, exposure profile, and hedge sensitivity. For portfolio optimization, PDEs appear in dynamic control problems, especially when the investor chooses control over time and the uncertainty, right? So that is what we have here. The lecture is actually teaching you 5 ways to attack your PDEs, right? Method 1 is separation of variables, which is like split time and state. Quant finance uses heat equation, Black-Scholes intuition. Method 2 is about characteristic, follow the path of information, which is for transport, PDEs, and forwarded dynamics. Method number 3 is Green's function, which use your impulse response, which is for pricing kernel expectations formula. Method number 4 is FDM or Frank-Nicolson, which is solve on a grade, which is option pricing, Greeks, hedging. Method number 5 is FEM, which is finite element method, solved on flexible mesh, complex domain, multi-factor model. The most important conceptual bridge is that PDE method is used for pricing or hedging or risk and dynamic optimization. In simple words, PDE tells us how values evolve, analytical method gives intuition, numerical method make the model usable in real markets. Okay, that is what we need to understand and remember. Okay, that's it, guys. That's what complete this chapter. I'll see you in the next chapter. Go back, revise it, but you have to understand this chapter. This chapter is very, very tough. One of the toughest chapters we have seen till now, right? So go back, understand it, read at least twice or thrice. You have to write down all the equations, you have to solve this, understand the meaning, understand the financial interpretation, understand the complex logics. Once you do that, then only you will be able to make sense of what is going on here, right? So go back, revise it at least twice, thrice, then only you'll be able to handle it, okay? That's it, guys. That's it from my side. I'll see you in the next lecture. Thank you.